This circuit is supposed to acquire the sound output from a stethoscope, which completes to be a biomedical signal processing system. In stage 1, ICTL072 is used. It is a dual low-noise JFET input general purpose operational amplifier. It supports a voltage gain of 10 mV to 1 volt but does not produce any current. The op-amp is an audio amplifier which converts sound signals to an electrical signal that reaches the minimum level for further amplification. When the audio amplifier amplifies sound, it can add or remove subtle shades in character of the sound. In this circuit, the op-amp is a fixed-gain closed-loop non-inverting op-amp. It's non-inverting as the input is put to the positive terminal of the op-amp. Capacitor C1 is a coupling capacitor that blocks any DC bias voltage from the input. Resistors R6 and R5 form a voltage divider that reduces the input voltage to 4.5 V as seen by these calculations. It also acts as a middle reference to the op-amp which is working in single supply mode. As the op-amp is in single supply mode, all negative portions of the waveform will be cut off without R6 and R5. With R6 and R5, since it is a level shifter, the entire waveform will be shifted upwards by V2 so that there is no more negative portions, so no waveform will be cut, which is what we want. Resistors R2, R3, and C2 and C3 form the bandpass filter with a passband gain of 1 plus 220 over 10K, which is equal to 23. The bandpass filter rejects DC voltages so that V2, which is 4.5 V, will not be amplified as well. Finally, capacitor C4 is a coupling capacitor that couples the output from the first stage by removing any DC input offset and allowing the AC signal to pass through. For testing, the power supply DC source is set at 9 volts and connected to the circuit. The function generator is set at 1 kHz and a VPP of 200 mV PP. The input is put to before capacitor C1. Channel 1 probe is put to test point 1. Channel 2 probe is put to test point 2. Giving us these values for 1 kHz. Based on the values earlier, I filled up this table. As you can see, we do get the gain value that we calculated earlier. I've plotted this frequency response curve based on these values. The negative 3 dB line is at 24 dB, and FL is 16.25 Hz, and FH is 1375 Hz. The bandwidth, which is FH minus FL, is equals to 1358.75 Hz. In stage 2, which is from test point 2 to test point 3, the IC used is the same IC which is used in stage 1, which is test point 1 to test point 2. Based on the schematic diagram, the amplifier is a negative feedback closed-loop inverting amplifier. It is inverting as the input is connected to the negative terminal. The negative feedback loop means some of the output voltage is returned to the input with a phase inversion. This means the input and output waveforms should be 180 degrees out of phase. Resistors R9 and R10 form a voltage divider so that the input voltage is 4.5 volts, which is the same working. It also functions as a level shifter, and it also puts the op-amp in a single supply mode. The level shifter works similar to stage 1, which is like this. For testing, stage 2, the function generator is set at 1 kHz and 4 VPP. It is this red wire. The power supply, the DC power supply, is set at 9 volts. The probe for channel 1 is put to test point 2, which is this white wire. The probe for channel 2 is put to test point 3. As you can see, the waveforms are 180 degrees out of phase between the input waveform and the output waveform. As I turn the trimmer, you can see the waveform getting amplified until it becomes saturated, and then it becomes cut off. The waveform being cut off is the part where it flattens out. The value of the output right before it cuts off is 6 volts, as you can see. In stage 3, which is from test point 3 to test point 4, firstly, you have capacitor C5, which blocks DC and allows AC. Next, you have resistors R12 and R11, which is a voltage divider which puts the IC in single supply mode. It also acts as a level shifter to make sure no output is being clipped. The op-amp is patched as a Salon key second order low pass filter. It is made of 2 low pass RC networks. Capacitor C7 will provide the feedback for shaping the response near the edge of the passband. The circuit allows low frequencies to pass through while filtering out the high frequencies. Output from IC2A will then pass through capacitor C8, which will filter out any DC. For stage 3, DC power supply is set to 9 volts, and the input function generator is at 5 VPP and 20 Hz. The input function generator is this red wire that I just attached. The probe for channel 1 is put to test point 3. The probe for channel 2 is put to test point 4. Giving us these readings for 20 Hz. Based on the values from earlier, I filled up this table. As you can see, when the frequency is at 500 Hz or lower, the filter is at unity gain, which means the gain is 1 or close to 1. Higher than 500 Hz, the gain starts to drop, as you can see. Based on these values, a frequency response curve was plotted. Based on the curve, the negative 3 dB line is at negative 3 dB from 0 minus 3. FH is equals to 1000 Hz, as you can see. The bandwidth is equals to FH minus FL, and since FL is 0, the bandwidth is equals to FH, which is 1000 Hz. Based on the values of the resistors and the capacitor, we can calculate FC, which is 1 over 2 pi square root of R7 times R8 times C7 times C6. When this is equated, you get 995.925 Hz. This is very similar to the bandwidth that we got. Finally, for stage 4, the IC LM386N-1 is being used. It is an audio amplifier that drives a speaker. It is designed to be working in single supply mode internally, so no voltage divider is required. The amplifier drives current to power up the speaker. Capacitor C15 filters out high frequencies that are above 40 kHz. Capacitor C13 will then block out DC and allow only AC to pass through. The input will first go through a trimmer, where pin E has full amplitude while pin A and pin S have zero amplitude of the input waveform. By adjusting trimmer 2, we can control the output. Hence, trimmer 2 can be considered as a volume knob. For stage 4, the DC power supply is at 9 volts and the input function generator is at 200 Hz, 200 millivolts PP, which is this red wire. The probe for channel 1 is connected to test point 4, as seen here. The probe for channel 2 is put to test point 5, as you can see. By adjusting the second trimmer, we can control the output of the second IC. The third IC, I mean. As the trimmer is turned, the waveform will become cut off. The output voltage just before the waveform becomes cut off is 8 volts, as you can see. Finally, to test the whole circuit, the DC power supply is at 9 volts and the function generator is at 200 Hz, 200 millivolts PP. The probe for channel 1 is connected to test point 1. And the probe for channel 2 is connected to test point 5. As you can see, the input and output waveforms are 180 degrees out of phase because of the inverting op-amp in stage 2. Turning the first trimmer does affect the output waveform, as you can see. And turning the second trimmer affects the output as well. The final output just before cutoff is 6.8 volts.